Hello, good morning here in the Philippines. A very beautiful morning today, and good evening in the United States and the other parts of the world. Greetings from the Astronomical League of the Philippines. I am Dr. Jet Aguilar, and I will be hosting today's webinar. And thank you so much for joining us for our 2024 Astronomy Expert Speaker Series. I am very happy to welcome all our attendees, not only from the Philippines, but also from all the other parts of the world. Today, we have another very exciting and interesting topic to be discussed by none other than Dr. James D. Lowenthal, who will speak on the topic, Bright Galaxies, Dark Skies, on the very interesting topic on the formation and evolution of galaxies. Dr. Lowenthal is a professor of astronomy at Smith College in Northampton, Massachusetts, and my colleague from ALP, Ms. Imelda Joson, will be introducing our esteemed speaker later. For those who were not able to register, but would still want to watch, we are currently live streaming on Facebook at the Facebook page of the Astronomical League of the Philippines, where you can view this webinar live. Before we start, kindly allow me to explain some rules for this webinar to help us make this an enjoyable learning experience for everyone. Please listen and do your best to give your undivided attention to our speaker. There will be a short question and answer session at the end of the presentation. You may type in your questions under the Q&A tab found in your Zoom interface at any point during the presentation. We'll do our best to read and answer your questions live after the lecture or via the Q&A tab. We would like to remind everyone that the contents presented in this webinar will remain as the individual property of the lecturer and the photographers in the presentation. We will also be distributing certificates of attendance via email to all registered attendees who will be present with us throughout the webinar. So please use the name you have written in your registration forms to help us facilitate this process. So enjoy the webinar and let us all have fun learning. Here's the program flow for the webinar. Now, may I turn you over to Imelda to introduce our speaker.
Thank you, Jet. And tonight, as Jet said, we have a very special speaker. So Edwin and I will both be introducing him. Well, see, when we were very young in the Philippines, living in the Philippines at that time, we were preparing for an eclipse expedition that we organized with the Philippine Astronomical Society. And one very helpful book for us was a book called The Hidden Sun, written by our speaker, who was then a student, an undergraduate student at Yale. And so he wrote this book in 1984. And unbeknownst to us that about 28 years later, we will have the opportunity of meeting our speaker
in person.
And when the following meeting, we had him autograph the book. And he wrote, January 6, 2014, to my new friends, Edwin and Imelda, whose work inspires me. See you in the shadow of the moon, or the AAS. And this was in Washington, D.C., James. So he was still very, very young, and that book helped us. The title is The Hidden Sun, Solar Eclipses and Astrophotography, a basic step-by-step guide. And a lot of people in the Philippines at that time, this was available at National Bookstore, bought a copy of this book. And it helped us have a successful expedition in 1988 in Mindanao. And so I will turn it over to Edwin to give the more formal introduction.
So thank you for the book, James. We really appreciate your help. Now, as Imelda has as our moderator had mentioned earlier, Dr. James Lowenthal is a professor of astronomy at Smith College in Northampton, Massachusetts. His research interests include high-redshift galaxies, Lyman-break galaxies, starburst galaxies, millimeter and submillimeter wavelength galaxies, galaxy formation and evolution, QSO absorption line systems, QSO host galaxies, and ultra-faint radio sources. James has used some of the largest telescopes in the world, such as Keck, Hubble, Spitzer, and the Large Millimeter Telescope in Mexico. James received his bachelor's degree in astronomy and physics from Yale College in New Haven, Connecticut in 1986, and his PhD in astronomy from the University of Arizona in Tucson in 1991. James served as vice president of the American Astronomical Society from 2016 to 2019. So, ladies and gentlemen, please welcome our esteemed speaker for tonight, Dr. James Lowenthal.
Welcome, James. We can try
much.
your slides again. Sorry. Yeah.
Thank you so much, Edwin. Thank you, Imelda. Thank you, Jose Aguilar. And thank you, everybody from the Astronomy League of the Philippines. You're so kind. It's only, it's a little embarrassing to be dragged through ancient history in that way, but you're very kind, and I'm glad that it was of any help at all to you. I have to say, looking at the video you just showed of all the eclipses that you all have been to and photographed so beautifully, I have a lot to learn from you. So congratulations. And it was nice to see Edwin and Imelda featured there for their asteroid and for their own book. And lots of congratulations right back to you and for all of your accomplishments. Let's see if I can try to reproduce what you taught me how to do. How does that look now for you all?
I can see the first slide.
Good.
Great.
Let's see if we can continue then with a little bit about me. And in case you have not had the pleasure of coming to the state where Imelda and Edwin and I all are right now, the state of Massachusetts in the United States. This is the northeast of the US, with New York City down at the bottom and Boston and Massachusetts in the middle. And my small town of 30,000 people, Northampton, is right in the middle there. And if we zoom in, you'll see that there are actually 5 different colleges located within a few miles of each other. And by college, what I mean is a university for undergraduates. So it's a particular kind of American thing, this so-called small liberal arts college that Smith is an example of. We are in a consortium with 5 institutions, 4 of them small colleges like mine, plus the University of Massachusetts, which is a big research university with 30,000 people. And they're all, as I say, a few miles from each other, connected by a free bus, and the students can take classes at any of the institutions. We're in an especially lovely part of the United States. This section of New England has a lot of rich history and culture, a lot of agriculture. Running right on the border of Northampton is the largest river in New England, which you see here, the Connecticut River. And it runs through some of the richest farmland in the United States, the former floodplain of the Connecticut River. Our 5 institutions have a joint astronomy department. Smith College, where I am, has its own department, very small, only 2 of us on the faculty. But we are part of this consortium, the 5 college astronomy department, that is much bigger, with 20 faculty. It's the institution that conceived of and developed the famous 2MASS project, the 2-micron all-sky survey. It is UMass and the 5 college astronomy department that have joined with the government of Mexico and built the 50-meter large millimeter telescope on a mountaintop in Mexico. More about that shortly. This is just to give you a little bit of context for some of the astronomy that happens here in this corner of Massachusetts. Smith College itself started in the 19th century, very small in this building. That was the building on the left, the brick building, was the only building there was at the time. And now it's got many more buildings, including the very modern one you see there, that's the campus center. It has always had astronomy. And here you see from roughly 1890, a photograph of astronomers at Smith College, students at Smith College, using the transit telescope that would observe the stars transiting the meridian, and the telescope is focused directly on the meridian. It moves up and down only, and it was used to set the clocks. And it was the main timekeeping system for our town of Northampton. They would observe the stars, set their clocks, and then relay the information to the train station, so that, of course, the trains would be able to avoid colliding by keeping accurate time. So Smith itself, founded in 1871. It's around 2,500 students. Here's the key thing: they're all women. It's a university for women, undergraduate university for women. It is part of a famous, in America, famous group of similar women's universities called the Seven Sisters. So we might imagine them as the Pleiades. And you may have heard of some of these. Radcliffe was the women's college at Harvard University. And some of these are no longer women's colleges, but Barnard and Bryn Mawr and Mount Holyoke and Smith and Wellesley remain women's colleges. Astronomy is one of the original 7 liberal arts from antiquity, which liberal arts colleges like ours look to, were inspired by. So Smith has always had an astronomy department. It's a private school, but it supports well over half of their students with significant financial aid. I'm sure you all know that the cost of a private education in the United States is ridiculously high, but I'm happy to say that Smith has very generous support for many students. So much so that roughly a quarter of our students are first-generation students, meaning their parents did not go to university or college at all, and maybe they come from very modest means, but still are able to attend Smith because of the support. Over 10% of our students are international students, including, of course, some from the Philippines. Some of the graduates of Smith College include people who are famous in the United States, maybe not so famous elsewhere in the world. Julia Child is a famous chef who had a television show. Gloria Steinem is an activist, supporter of women's rights. Sylvia Plath, a poet and author. Madeline L'Engle, the author of A Wrinkle in Time, a book that maybe some of you know. Nancy Reagan, the former, the wife of the former president. Barbara Bush, the wife of the former president. Julie Nixon, the daughter of the former president. Our little astronomy department at Smith consists of just me and my wonderful colleague, Dr. Kim Ward Duong, who studies low mass stars and exoplanets. Now, on to the subject of my talk. We are now in Chaco Canyon in New Mexico, in the southwest of the United States. And that was the Milky Way passing across, and that's Mars setting behind the cliffs that the ancestors of today's Pueblo Native American people would have seen in much the same way. This is one of the darkest skies in the United States. And it is such a deep privilege and a pleasure to stand there in full darkness and realize that the ancient Puebloans, the ancestors of the Diné, today's Navajo people, looked at the same stars and saw the same view, and they revere this place as the origin of their people. In much the same way that the Seneca Indians, the people close to where I live here in Massachusetts, who lived here for thousands of years, looked to the sky and saw the Milky Way as a path to the sky that the deceased humans would take, following the stars as stepping stones and the Milky Way as a path to the next life. Of course, many ancient cultures looked at the Milky Way and saw it as a path to the sky, perhaps associated with milk. So many cultures called it milky in some way or another. In Spanish, or in Latin, or in Italian, la via lactea. And of course, the word milky is in the word galaxy. Galaxy and galactos and lactose all come from the same Greek roots. So it's in so many thousands of years of our history worldwide to see that path as associated with milk, or a path, or some combination of the two. And here again is our own Milky Way. We now know, of course, that path of Milky Way is the combined light of 100 billion stars spread out in a path, a circle around the entire sky. It's the pancake, the disk that we are in the middle of. All the stars in this picture are members of our own Milky Way galaxy. But of course, sharp eyes among you will notice this smudge there. That is the one thing in this picture that's not part of our Milky Way. It's our neighbor, the Andromeda Galaxy. Here it is, 2024. 100 years ago, in 1924, another Edwin Hubble, discovered Cepheid variables, which Henrietta Leavitt had shown could be used to estimate the distance. A particular kind of variable star, blinking stars that are, it was realized, thanks to Henrietta Leavitt's work, extremely useful distance indicators for larger distances than were previously possible. And Edwin Hubble used this new technique to identify Cepheid variables, blinking stars in the Andromeda Galaxy that were so faint they could be explained only if the Andromeda Galaxy was some 2 million light years away, over 20 times the size of our own Milky Way galaxy. Clearly, the Andromeda Galaxy was separated from the Milky Way by a giant gulf of space. Extragalactic astrophysics had been born. The big question then that motivates much of my work and much of astrophysics today is this: how did galaxies like the Milky Way and Andromeda form? How were they made? How did they evolve to become the mature spiral galaxies we see today? By the way, some of these pictures were taken with my own homemade 6-inch telescope in my backyard here in Massachusetts, this one included. I started as an amateur, as Edwin and Imelda described. I became a professional, but I've never left my amateur roots. I still use that telescope in my backyard today. What then is the fate of galaxies like this one, the Whirlpool Galaxy? This picture does actually provide one important clue. You can notice that smaller secondary galaxy just above the main spiral. That secondary galaxy is massive enough and close enough that its gravity has pulled a trail of stars and gas and dust out of the main galaxy's body. These two galaxies are in the process of merging to become one more massive galaxy. And that's an important clue. Here are two more neighbors of the Milky Way in the constellation Ursa Major. You amateur astronomers will recognize these, of course, as M81 and M82. They're very similar to the Milky Way and Andromeda. They're so close to each other that they're in a gravitational dance. And I took this picture when there was something special happening, a supernova in M82. There it is, a star dying in a violent explosion. Now, this is not the first time that a supernova has been observed in M82. Why is it that we are able to observe multiple supernovae in M82 in a short period of time when in the Milky Way, we haven't seen a supernova in hundreds of years? And the answer is because M82 is being tugged on by M81's gravity. And that pushes and pulls on the gas in M82, funneling it down into its center like water going down a drain, where it's getting compressed and turned into stars at a furious rate, 10 times the rate of the Milky Way. So that galaxy on the left where the supernova is 10 times smaller than the Milky Way, but it's producing stars at 10 times faster rate. So per unit mass, that's 100 times more star formation. This is what we call a starburst galaxy, a galaxy that is very quickly turning its own gas into stars. When you make new stars, especially a lot at once, some of them, the rare ones, will be very massive, and massive stars die young as supernovae. So there are many supernovae in a starburst like M82, and then something happens as a result. Not only is there gas being pulled into the center by the gravitational interaction with its neighbor, but there's also gas getting pushed out. And this is a Hubble Space Telescope picture of M82, where the gas, you can see that the gas is actually getting pushed out of the galaxy. It's what you might call an exploding galaxy, and sometimes it is called that. That red light of the red in this image is, of course, the light of hydrogen alpha, and it shows ionized gas that is being pushed out by the supernova activity in this galaxy, the starburst activity. This kind of gravitational interaction between galaxies is a common enough occurrence that we see many other examples of merging galaxies spread across the sky. And here is a Hubble Space Telescope of two such massive galaxies connected together by a stream of shared stars and gas that are getting pulled between the two galaxies as they spin closer and closer together in a sort of death spiral. This process leads to these long linear features that we call tidal tails, because they are due to tides, meaning the gravitational effects of two massive objects close to each other. And it also leads to starbursts at the same time. Here in the antennae galaxy, obviously called that way because they look like the antennae of two bugs, or one bug rather. We see a pair of galaxies in the process of merging. If we take a close-up look, we can look into the heart here of these merging galaxies, and we see right away tremendous star formation. All that pink light there is light of gaseous nebulae, gas clouds, excited by the brand new stars that are being formed here at a rate higher even than M82's. So not only do we see these tidal tails of gas getting stretched out, but then in the core of the merging galaxy pair, we see a tremendous starburst. Now you might notice, in addition to the pink color and the blue is the light of brand new stars, the pink is the glowing gas around them. What's that brown stuff? Why are there brown lines? Why is any of the light brownish here? And the answer is, we are looking through dust. We're looking through a kind of smoke screen that almost always accompanies regions of star formation. The middle of this starburst galaxy, if it weren't for that dust, would be thousands of times brighter. You might know that the same is true of our own Milky Way galaxy, in the sense that if you look towards the constellation Sagittarius, you do not immediately see a spectacularly glowing bright ball in the middle of the galaxy in the constellation Sagittarius. Instead, you just see sort of normal Milky Way with a slightly higher density. The reason you don't see clear to the middle of the galaxy, of course, is because there is significant dust in our own Milky Way that dims the light by a factor of many millions of times. Likewise, here, the optical light, the light that we could see with our eye, is mostly absorbed by this brown, smoky dust screen around the starburst. Okay, then, to summarize, a collision of two gas-rich spiral galaxies, especially ones that have dust in them, like the Milky Way and Andromeda, if they collide, that will trigger, and this is going to happen 5 billion years from now when the Milky Way and Andromeda collide, can trigger a huge burst of star formation. And when the dust that surrounds that star formation absorbs the optical and ultraviolet light produced by those new stars, that dust then glows in infrared. This process can also make a new galaxy. The glow in the infrared is going to turn out to be a critical piece for the rest of the story of the high redshift, the very early universe galaxies that I study. So here again is the pair of galaxies we saw first, and the antennae second, and the close-up from Hubble of the inside of the antennae galaxy. Now, wouldn't it be great if we could really understand the details of how these galaxies merge together? And we can't see it happen in real time. We can't see it unfold because the sizes and the distances are too great and the speeds are too slow compared to human lifetime. But we can simulate it in a computer. And here, let's watch a computer simulation of two colliding galaxies. This simulation made by my colleagues, Chris Mijos and Lars Hernquist and Frank Summers. The video is a little bit glitchy, but so it's not very smooth, but I think you'll probably get the picture. And you'll see that these two galaxies, as they merge together, form different shapes that often look just like the shapes we see in the sky of merging galaxies. So there's a Hubble picture, and now back to the simulation. And look, and there's another Hubble picture. So the simulation is able to reproduce multiple different sources that we see in the sky. Here's the simulation again from a different angle, and there is a real pair of merging galaxies in the sky. So we are able, with clever computer programming, to reproduce this incredible diversity of shapes we see in the sky from merging galaxies with their tidal tails and their dusty, gas-rich, star-bursting cores. So we think we understand the dynamics, the way that gravity drives the gas and the stars together in these mergers. We understand how they're dominated by the dark matter that we can't see, but we know is an essential ingredient in these simulations. It doesn't work unless we include dark matter. So, in fact, let's build a bigger simulation, a more general one, not just of merging galaxies, but of the formation of a galaxy. Here we're watching a simulation called TNG50, the Next Generation 50, a collaboration of dozens of astronomers around the world using supercomputers, crunching away on millions of theoretical dots of gravity, points of multiple stars and gas and dark matter, collecting together over billions of years. And you can see the clock ticking in the upper right. This is now 3.5 billion years after the Big Bang. You can see the scale on the left, 300,000 light years, so that bright disk in the middle is going to be a Milky Way galaxy. And as we rotate around, you see, sure enough, there are spiral arms. This computer simulation has made a spiral galaxy just 4 billion years after the Big Bang. And yet you also see how messy this process is. The main picture, the colored pink and purple panel, is showing gas. The lower left panel is showing dark matter and then gas. And the lower right panels are showing a zoom in of the stars in black and white and the gas in color. And there's no way you can look at this and not come away with the understanding that galaxy formation is complicated. This is a messy, complicated, stochastic, random process driven by gravity. It's gravity that's pulling it all in, but there's also a lot of gas physics and what we call feedback, where stars are forming, supernovae are going off, gas is getting pushed out of the galaxy. Perhaps there's a supermassive black hole in the middle turning on, and shining so brightly that it also pushes gas away. And meanwhile, gas continues to rain on, and you saw dwarf galaxies rain down onto and collide with the main galaxy. So very, very complicated question. This is trying to get at that big question: how do galaxies form? How do starburst galaxies form? What can starburst galaxies in particular tell us about all galaxies? Did the Milky Way go through every stage of galaxy formation that we just saw, or only some fraction, some subset of those processes? How are we going to answer this? Well, first we need to find the galaxies to study them. This picture shows mostly stars. Almost everything in here is a star. This is a section of Ursa Major. Sorry, that's not true. This was a section of Orion. We're going to zoom in here in a section between Lepus and Cetus. So let's zoom in and watch what happens as we look deeper and deeper into space. And we'll see that the space between the stars starts to get filled in. Oh, the movie is not showing in my Zoom screen. I don't know what you can see. Maybe can somebody tell me, do you still see the constellations?
Yeah, we can see the constellation, but there's no animation.
Yeah, something has happened with the Zoom and PowerPoint, the way they're interacting, and it's not actually showing the zoom in. Let me try it one more time, and if it doesn't work, that's okay. I'll just explain what it was showing. This is the section of the sky that contains the Hubble Ultra Deep Field. It's a tiny little patch of sky right down in the middle of this picture. This is all stars, but if we zoom in, and we point a telescope like Hubble at this little patch of sky that corresponds to a grain of sand at arm's length, just 2 arc minutes on a side, then we will see 1,000, 2,000, 3,000 galaxies in a tiny little patch of sky that I'll show you in a still image in just a second. So the animation didn't work, I'm sorry. But what we're able to do then is map thousands of galaxies, hundreds of thousands of galaxies, millions of galaxies, to map them across the sky and even to measure their distances, which then gives us the 3rd dimension. The sky seems like only 2 dimensions, terribly important, but even more important to measure it in 3 dimensions. We do that using telescopes equipped with spectrographs that measure the Doppler shift, the redshift of galaxies, showing the expansion of the universe. And the nature of the expanding universe is the farther the faster. So a galaxy that is showing more redshift is farther away. That lets us measure its distance. Once we've done that, we can put together a map like this one. This map shows the Earth and you and the Milky Way and Andromeda and M81 and M82 all right down there in the middle. This map is assembled by the Sloan Digital Sky Survey. It's a slice of the universe out to 2 billion light years away. A good fraction of the way back to the Big Bang. And every tiny little dot in this picture is a galaxy. So we're seeing here thousands and thousands of galaxies mapped out across billions of light years. And you can immediately see that the structure of the universe is not random. They're not just randomly laid down. Instead, there are filaments and bridges between clusters of galaxies and superclusters of galaxies. The Sloan Digital Sky Survey went further and put together here a video using that distance information available. So these are actual Sloan Digital Sky Survey images put together in this video using the redshift information and therefore the distances to build a 3D fly-through of the universe. So here we are flying through thousands and thousands of galaxies, and you can just enjoy the ride and see the structure of the universe. Again, you see filaments and strings, and we can also appreciate the diversity of galaxies. Most of them are disk spiral galaxies like the Milky Way, but many of them smaller, some bigger. We also see, however, elliptical galaxies that don't have a disk or spiral arms. And I'm sure many of you are familiar with the nearby Messier objects that are elliptical galaxies. And we see them especially in clusters, like the ones that are coming and going in our view here of this Sloan flyby. This simulation from the Millennium collaboration shows us several billion light years of universe in a box simulated in the computer with 10 billion particles crunched by the supercomputer for weeks of time to simulate what the very large scale structure of the universe looks like. And you see here, it looks like a sponge or froth or foam. The universe has this foamy, frothy texture to it with voids, thousands of light years across, or sorry, millions of light years across, voids where there are no galaxies, and then strings where there are high concentrations, again, connecting these clusters of galaxies. Now, why is this so important? Because this is the context for where galaxy formation and evolution happens. If we don't understand this big picture, then we can't understand the more detailed picture that happens within it. This picture is also made of dark matter and gas and stars. It's dominated by the dark matter. It's also influenced by dark energy, the strange sort of anti-gravity that is pushing the universe ever faster apart. If we don't understand all of that well enough, then we can't take the deep dive to understand how galaxies themselves form. So here we are back to another sort of close-up, and this is what I was hoping to show you in the zoom in from the region around Orion and Lepus. This is the picture that Hubble sees looking at a grain of sand held at arm's length, just a couple of arc minutes, thousands of galaxies in one shot. And all of these dots in this picture, except for a very few, for example, I don't know if you can see my cursor, but this bright one at the lower right that has spikes through it, that's a star. Almost everything else is a galaxy, each one with roughly 100 billion stars. Each of these galaxies is far enough away from us that we are looking back a significant amount of time, millions, at least, usually billions of years back in time. That's long enough back in time that each of these galaxies is showing us a baby picture of itself. None of these galaxies looks exactly like this anymore. We're looking back a significant amount of cosmic time to see them. Some of the galaxies in this picture are more than 90% of the way back to the Big Bang in time. So we're going to use this cosmic time machine to look back and see if we can see how early starburst galaxies form. But how are we going to find them? Here's the goal. We want to find the equivalent of those merging galaxies, or M82, or the antennae galaxies, or ARP-220, or the other super duper starburst galaxies we see near us today, near the Milky Way. We want to see if those existed in the early universe as well. How are we going to do that? Well, one way we can do it is by turning our best optical instruments. I showed you the Hubble Ultra Deep Field before. Here now is the Webb Space Telescope, James Webb, JWST, I'll call it from now on. JWST's picture of the same part of the sky. And in fact, we can take this all JWST picture here and see that, in fact, it had a two-camera view. It's got a bigger field of view than Hubble, and it goes much, much deeper. So that if we zoom in, we see there are just galaxies upon galaxies upon galaxies. And even those big spirals that look as if they're nearby, those are billions of light years away. The little tiny smudges, much, much farther still. We have this incredible capability to look back in time using the dramatic powers of JWST in the optical, but especially in the near infrared. And one thing I want to draw your attention to here is these funny sort of linear features. Not the blue one, that's a star with the diffraction spikes, but these features here, these reddish lines and these reddish curved lines, and these lines here, and these lines here, and these lines here. What we're doing here is looking at deep space. We're looking at the distant universe, say 10 billion light years away, right through a partly transparent massive cluster of galaxies at an intermediate redshift, an intermediate distance, say 5 billion light years away. That massive intermediate cluster of galaxies, with maybe 1,000 times the mass of our Milky Way, is lensing space-time. It's warping space-time, bending the light of the more distant galaxies so that they look like those funny linear features. That is not the way the galaxies actually are. It's just how they look when we peer at them through the gravitational lens of this intervening cluster. The great thing about it is the lensing effect makes those distant galaxies look brighter, which makes them easier to detect and to study. That view was in the optical. But didn't we say that the problem with dusty starburst galaxies is all that dust? They don't really show up in the optical very well. They're not that bright. They're really bright in the far infrared, where the dust is glowing. Then what we should do is turn not our optical visual eyes on the sky, but our far infrared eyes. So let's do that. We'll use the European Space Agency Planck satellite. The Planck satellite was launched by the European Space Agency with the main goal of making a map of the entire sky in microwaves, short wavelength radio waves, from around 300 microns wavelength out to about 11 millimeters wavelength. The whole goal was to study the microwave background, the leftover radiation from the Big Bang. It did that, and here is that map in detail that had never been seen before. Every little red spot here is a slightly hotter part of the very distant universe, just 100,000 years after the Big Bang, looking back more than 13 billion years in time. The blue spots are cold spots. The red spots are going to become galaxy clusters, that structure that we saw in the previous flyby. So Planck did a splendid, spectacular job of making an all-sky map of the microwave background. But along the way, lucky for us, it also made a map of 100,000 point sources that are not part of the microwave background, point sources that are mostly nearby galaxies or even things within our Milky Way galaxy. But some of them are distant galaxies. And my colleague and friend Min Yun at the University of Massachusetts is an expert at finding in the Planck maps, in the Planck database, and I'll show you here the point sources. This is the map not of the microwave background, but of the point sources found by Planck. And you see the red line in the middle there. That shows you the points in the Milky Way galaxy itself, but all the other points, most of them are outside the Milky Way. Min Yun is expert at sifting through the data set of hundreds of thousands of targets and finding the rare objects that are most likely to be distant star-forming dusty galaxies. And that's exactly what he did. He found a sample of about 100 of them, which then needed to be followed up to prove that they were actually distant galaxies. The first thing we tried was to use the large millimeter telescope, the 50-meter diameter telescope on top of this volcano in central Mexico that was built, as I said, by UMass, the University of Massachusetts, in collaboration with the government of Mexico. It sits on the shoulder of the tallest mountain in Mexico. You see them both here. On the left, Sierra Negra, Black Mountain, and on the right, Pico de Orizaba, 6,000 meters high. Sierra Negra on the left is 5,000 meters high. It's in the middle of Mexico on the plateau between Mexico City and Veracruz in the state of Puebla. I've been very fortunate to be able to go there many times and to visit our sister institute, which is shown here. This is the Instituto Nacional de Astrofísica, Óptica y Electrónica, INAOE, and it is our sister host of the large millimeter telescope. And from there, you can see volcanoes in multiple directions, including here the volcanoes that are directly outside Mexico City. This is Popocatépetl, and it is so close that sometimes it rains volcanic ash down on that part of Mexico. Here we see the dormitory a few hours away from that institute, close to the mountain where the telescope is, where we spend our days sleeping when we're observing at the telescope. And there's a full restaurant, and it's a lovely experience to enjoy the hospitality of the local people in central Mexico there, who take such good care of us when we're observing. This is in the town of Ciudad Cerdán, where the view is dominated by this dormant volcano, Sierra Negra, with the LMT on the summit. And I here want to show you a little bit more of what it's like to go observing there. Fortunately, it's not like this. This is Popocatépetl again, the volcano outside Mexico City, which, as I said, is often erupting. But our volcano is not. It's a dormant volcano where we feel confident with our telescope. It's, as I said, right next to Pico de Orizaba, which has a name in the local language, Nahuatl, Citlaltépetl, Star Mountain. So you get in the van in Ciudad Cerdán, and you head out for the 1.5-hour drive up the mountain. Here is a different view of a different star mountain. Here is our star setting behind a local mountain. As you work your way up the mountain, you might find yourself in fog, and you might find yourself in a cloud of sheep, because there's a lot of agriculture in the area. This is a truck full of workers on their way up the mountain to work on the telescope. And before long, you are in alpine country and looking at snow on above the snow line, and maybe looking down across hundreds of miles of mountains towards Oaxaca in southern Mexico. And look to the lower left, and you'll see this road snaking up the mountain. This is the tallest, highest altitude road anywhere in North America, up to 5,000 meters. And it's a dirt road with no guardrails, and it is quite an experience driving around each of those turns one after another, sometimes late at night or early in the morning, with no guardrails. Just a little bit worried about every turn. But when you get to the summit, what a view it is. And here you'll all recognize the shadow of the Earth rising up the blue band beneath the pink band as the sun sets in the opposite direction. And you see some of those volcanoes in the distance on the horizon there, looking back towards Mexico City. Or you might notice the shadow of our own volcano. Here we are standing on the summit of Pico de Orizaba with our back to the sun, as the shadow of the mountain, the volcano, rises up into the sky. And it's such a pleasure to enjoy this spectacular view, and the privilege of the sunsets and the sunrises and the views is something I really treasure and look forward to the next time. Maybe you get to the telescope at night, in which case you'll pass through the gates and see a view something like this. Our new 50-meter Gran Telescopio Millimetrico, or large millimeter telescope. Or maybe you get there just at sunset, as the sun sets on the flank of Pico de Orizaba. And it's interesting to think that as we look at this snowy mountain, there are mountain climbers on that mountain right now. And you can't see them, but we'll see them shortly. The telescope itself, seen from the back here, is about 25 stories high. It's an enormous building. For scale, look at the bottom, you'll see a car and a doorway there. Here, two of my colleagues standing at the base of the telescope give you a little sense of the scale. And here I am at the doorway, dwarfed by the telescope over our head. You'll notice the fog here. The weather can be terrible at times. It can snow any time of the year. This picture is in the middle of our summer in July. But at this elevation, a foot of snow is not uncommon, even in the middle of summer. Inside the telescope, the structure looks like this. And here, my colleague is standing on a part of the telescope that actually moves. Milagros is standing on the grate that rotates. The whole building rotates around the concrete pier, the cone that you see at the right side. So the concrete stays stable, and Milagros is going to be taken for a ride around that central cone as the telescope moves in azimuth. It's an ALTAZ, altitude azimuth telescope. You take an elevator up 20 stories to the control room. And here, Arturo Gomez Ruiz is sitting next to an undergraduate student, Erica Keller, from Mount Holyoke College in Massachusetts, who spent many weeks down there. She got so good at controlling the telescope that she just became the regular telescope controller. So there's $150 million telescope controlled by one undergraduate student. Very impressive. And here we are after a night's work and just enjoying the sunrise after staying up all night observing. Now, radio astronomers are a funny bunch, I have to say. They don't do what we optical astronomers do. We optical astronomers, we always go outside and look at the sky with our eyes, and we assess the conditions, and we let our eyes get dark adapted, and we make sure that that there are no clouds blowing through, and see if it's photometric or not. Radio astronomers, they don't care about that at all. They can measure the clouds with their instruments, and they don't really care what the optical quality of the sky is. So they spend almost the whole night inside. Not me. I go out and I soak in the incredible gift of a dark night sky. Here, brightened somewhat by a thin crescent moon, totally overexposed in this picture. But notice that there's this band of light below the moon. That's the zodiacal light, which you can see only in a really dark sky like this one. Here, I turned my camera on the sky for half an hour and recorded parts of Orion that I didn't even know existed, and the winter Milky Way arcing across this rich, black, beautiful, dark sky. And I like to take videos of the sky turning overhead and looking down 6,000 feet to the plateau below us. And here we're going to turn our heads towards Pico de Orizaba and look carefully for little glittering lights going up and down the mountain. Those are the climbers. Those are the headlights of the climbers making their way in the middle of the night up to reach the summit of the tallest mountain in Mexico just as the day breaks. And here you see the North Star sitting pretty low, pretty close to the horizon, just 18 degrees latitude where we are here in Mexico, similar to Hawaii. And while you in the Philippines may be used to seeing the stars turn around and axis very close to the horizon, for us Northerners, that's a special sight. And here we turn our view to the telescope that's right now tracking the stars. And when it looks up quickly, that's because it's doing calibration. Of course, this is a time lapse. It's speeded up. It doesn't move anywhere near this fast. But you see that the whole building moves. So that's a 1,500-ton structure that points to an accuracy of a few arc seconds. It's a phenomenal engineering feat. The dish itself is actively controlled because it weighs so much, 1,500 tons. It sags under its own weight under gravity, so it's controlled by active actuators that are constantly pushing and pulling on the surface to maintain its accuracy. We just saw the Milky Way spinning by, and here's a view of the southern Milky Way, which I loved being a northerner, but I also especially love seeing the clouds below us, passing past, streaming past the mountains and the traffic and the city lights below, far, far below, and then the sun rising. There are some clouds above us at this altitude, but not much. We're above more than 50% of the atmosphere, and a lot of the cloud deck layer is below us, which is what matters for millimeter wave astronomy. That's what we're doing here, short wavelength radio. And it's very sensitive to water vapor. We are above the great majority of the water vapor. And I just treasure this experience of being on this remote mountaintop, and I feel as if I'm literally seeing the stars fall into the telescope here in this view. Okay, we turned the LMT on our targets, chosen by the Planck satellite, to see if we could confirm that they were in fact distant, dusty starburst galaxies. And what did we see? In every case, a strong, strong signal. Here, the pink is, the pink contours are showing the brightness in this particular part of the sky from a different space telescope, the Herschel Space Telescope. But the grayscale is the image made by the Large Millimeter Telescope, the Aztec camera at 1.1 millimeter wavelength. And in every case, we see that black dot in the middle is the strong signal of a dusty star-forming galaxy. How do we know it's distant? Because the LMT also has a spectrograph, and we're able to get spectra. And here you see the spectra of some of these distant galaxies, confirming, in fact, they are very, very far away at redshifts of 2 or 3. You see the redshift shown by Z there, or even 4 in some cases. The red lines there and the sharp spikes in them are showing the light of carbon monoxide gas in galaxies more than 3/4 of the way, more than 90% of the way back to the Big Bang in some cases. Great, so we've confirmed that in fact we've found some of the most distant dusty starburst galaxies. The problem is we can't see the details we want to see. We want to see something like those mergers I showed you before. Are these mergers? I don't know. Why not? Because the telescope doesn't have the sharp vision that we need to resolve these images. They're just fuzzy blobs. What do we do now? Well, now we can turn to that phenomenon we saw earlier, gravitational lensing. Here's the concept. We are on the Earth in the lower right in this picture. The distant galaxy is in the upper left in this picture. If the light happens to be passing through an intervening cluster, which you see here, it says a galaxy cluster, then it bends space-time, and instead of following straight lines, the light will follow curved lines like the ones you see here, which is sort of like looking at a candle through a wine glass. And it bends the light, it changes the appearance of the candle. Instead of looking like a candle, it looks like a ring, but it also makes it much brighter. And we're going to use that effect. Here's a spectacular example of Hubble's image of galaxy cluster Abell 370. And all of those arcs, again, are gravitational lenses of distant galaxies lensed by an intervening cluster. We get to do the same thing with our galaxies. Why? Because it turns out all of our galaxies are gravitationally lensed, something we did not know at the beginning. These are collaborators, Min Yun, my former student, Olivia Cooper, Patrick Kamianeski. They are now some of the experts in this field. Here's how it works. Here is a video of an imaginary black hole. This is a computer simulation of a black hole passing in front of the Hubble Deep Field or the Ultra Deep Field, showing how galaxy images get warped into rings. And now let's look at what our galaxies look like, viewed through Hubble Space Telescope. Our LMT pictures were fuzzy. Hubble Space Telescope and ALMA, the Atacama Large Millimeter Array in Chile, have very sharp vision. What do they show of our galaxies? Gravitational lensing. They show a ring, just like the ones we saw a second ago, a ring that is not the way the galaxy actually looks. It's because it's strongly lensed by an intervening group of galaxies. Those red dots there are all one galaxy imaged multiple times into that ring shape. And the red dots are seen in the millimeter by the ALMA telescope. the green is seen by Hubble. Not just this one galaxy, every single one of ours turns out to be a gravitational lens. And it was so exciting. Every week or every month, I would get an email from Space Telescope saying, oh, we've observed another one of your targets, and here come the data. And I would download the data, and it was another so-called Einstein ring, a ring showing that each and every one of these was a gravitationally lensed distant dusty galaxy. Okay, great. We've discovered dusty starbursts in the distant early universe. We've shown that they're gravitationally lensed. Now what? Now we have to figure out what objects are doing the lensing. And that is a complicated disentangling project that Patrick Kamieneski, our graduate student, became a world expert at. In the grayscale here, you see those curves from the Einstein rings. In the red, you see possible explanations for where the intervening mass is that's doing the lensing. And we have to try and figure out which of those two is the right model. One way to help is to use the Gemini telescope to get more optical pictures to help us disentangle what is a foreground lensing galaxy and which is a background lensed galaxy. And here we're seeing a compilation. The colors here are giving a clue. The greenish galaxies are in fact the lensing cluster. The purplish ones are the background dusty star-forming galaxy that we're interested in. So then our job is to unscramble these, and some people in our team have become world experts at this, so that, for example, we turn the image on the left into the picture on the right that shows, you see the little diamond shape in the middle there, and next to it there's a little turquoise contour. That's what we think the galaxy actually looks like. Let's zoom in on that. This is now a close-up of what we think is the unscrambled view that the galaxy would appear if we were right next to it. Now we're beginning to get tantalizingly close to what we wanted to see. Are these merging galaxies, or is there some other reason that they're forming stars at 1,000, 2,000, 5,000 times the rate of the Milky Way Galaxy? All right, so we found that that most of our distant galaxies are in fact gravitationally lensed. Let me just remind you, this was by chance. We did not set out to find gravitational lenses. What I'm showing you here is the largest sample of gravitational lenses previously known, but that team had a goal of finding gravitational lenses. We found ours purely by accident, but then we get to use them. So we found some of the brightest galaxies in the universe, and they are made even brighter by the gravitational lensing. In the optical, you don't see anything bright at all because of all that dust that's wrapping up the starburst galaxy. But in the infrared, you see a spectrum here. That bump in the spectrum shows you lots of infrared light coming out. That's from the dust reprocessing the starlight. That redshift 2.5, Z of 2.59, tells you we're looking back 11 billion years in time. And when I say that these galaxies are among the most luminous in the universe, what do I mean? Well, the Milky Way is off the chart to the bottom here. The Milky Way is down below here on this chart. This chart shows redshift, meaning look back time. This is now on the left, and this is 13.5 billion years ago on the right. So these galaxies are further and further and further back in time. And up and down here is brightness. Up is brightness in units of the sun's luminosity. The Milky Way would be down below here at about 10 to the 11. Our galaxies are 10 to the 13, 10 to the 14, thousands of times brighter than our own Milky Way galaxy. So here's the summary of our ability to measure to use gravitational lensing to disentangle our starburst galaxies. In each case here, we see a sample of optical images, millimeter wave images, and then our computer models that have used the gravitational lensing to unscramble them and begin to see, oh, in fact, we do actually start to see things like rotating disks and multiple clumps and infalling gas that we're still in the process of analyzing to figure out how they power their monster starbursts. Some of them have active galactic nuclei, AGN, supermassive black holes in the middle. We can tell that by turning an X-ray telescope, which Daniel Wang and Carlos Garcia did. But most of them are powered by star formation. James Webb Space Telescope now lets us see better and better and better into the distant past to similar projects, similar fields like this one, where in fact 2A, 2B, and 2C are 3 images of one supernova that went off billions of years ago. We're just seeing now for the first time. This is a similar JWST image of a gravitationally lensed cluster that also has distant starburst galaxies behind it. And the expertise of people like Patrick Kamianeski have enabled us to build up these reconstructed images that we've never been able to see before, and finally see disk galaxies in the process of colliding just a billion or 2 billion years after the Big Bang. So I see I am at the end of my time, and I am not going to be able to tell you about the dark sky work that I do. I will just quickly bring us to the Philippines in 2012 and the Philippines in 2023, and share my concern that I'm sure you also have about the increasing light from LED street lights like this one outside my house, and about the increasing rates of health problems like cancer and diabetes and sleep deprivation, and the concern for the wildlife that light pollution is now threatening, and the concern especially for the loss of our night skies to the point where you can't see even the brightest stars of the Milky Way from the middle of my town anymore. So I had much more to say about this. I'm sure you do too, but I will just close with this simple plea to you to help us fix light pollution so that we all can continue to study the sky and enjoy looking out our windows to see the Milky Way, as this boy is doing in this lovely storybook by my friend Mordecai Gerstein. And with that, I will thank you all so much for your attention, and please go outside and look up and enjoy the Milky Way for me. Thank you, and I'm happy to take any questions if you care to.
Thank you so much, James. Wow, I would have loved to sit in one of your lectures in your class.
Well, you just did, I'm afraid.
Yeah. Let me just look at some of the questions here. Wait. There's one here.
I do see from Dante de Jesus.
Yeah.
Would you like me to read those?
Yes, please. Thank you.
Okay, so I see part 1 on electromagnetic waves.
Yeah.
Do magnetic fields and charged particles exist during the formation of early galaxies? Absolutely, yes. They definitely do. The physics of those early galaxies is not that different from the physics today. The universe had expanded so much that all the basic physics was, all the ingredients were baked in by then. The universe was, the stuff of galaxies was hydrogen and helium, just the way it is today. There were magnetic fields, the exact origin of which we do not know, but galaxies definitely had strong magnetic fields that we see the relics of today in the interstellar medium. Number 2, charged particles moving in single file that cut through perpendicular to magnetic field lines would produce electromagnetic. Oh, okay. I see. This is a long question. I better read the question more carefully. Sorry. All right. This is a much more involved question than I thought. Let's see. So that would produce electromagnetic waves, including visible light. Yes. If yes, the uniform speed of individual charged particles and their spacing in between will determine the resultant frequency of wave. Wow. Okay. This is not going to be in my field of expertise. I'm not sure I'm going to be able to answer this. Would the following be considered another version of magnetic reconnection? Head-on collision of unlike poles north and south of two speeding bar magnets. Is it right to say magnetic acceleration is magnetic potential energy being transformed to kinetic energy? Okay. I wish I could answer this authoritatively, but this sounds like something for a an astrophysicist who is more familiar with magnetic field propagation and cosmic ray propagation and production of synchrotron emission. So I'm familiar with all these issues, but I'm just not going to be able to give you an authoritative answer on it. So congratulations on the thoroughness of your question and your thinking, and I'm sorry that I can't answer it.
Yeah, actually, Mr. Jesus actually emailed me before I regard that he might be asking these questions, and I told him we can just ask. And
Sure.
yeah, but of course, because as we all know, study of galaxies illustrates to us a lot of astrophysical concepts. Anyway, thank you so much for trying to answer. I hope, Dante, that we were able to satisfy answering your questions. I just have a quick question here. Now, I've always been, this is just a sort of a layman's question.
Yes.
When we have this, how do actually you show this very beautiful animation, mathematical animation, computer simulation of galaxy formation. But I've been always been I am intrigued by how in spiral galaxies how those spiral arms actually form. What is the reason for the formation of the spiral arms?
Yes, it is now understood. Thank you for the question. It is now understood that spiral arms are a pattern of density waves. They are essentially ripples passing through the galaxy or around the galaxy, ripples that slightly compress gas and produce ripples of star formation that then shine brightly in massive stars, because whenever you make, if you take a cloud of gas and turn it into, say, 1,000 stars, you might get one very bright blue star and a few hundred medium mass stars and 1,000 low mass stars. The light will be dominated by that one bright blue star. And so you'll see bright blue spiral arms, which is what we see in spiral galaxies, but it'll be in a pattern. As the pattern moves through and around the galaxy, there will be a ripple of star formation. So what makes that pattern happen? Why is it so common? That is something that that has taken a long time to figure out, but it seems to be that the shape of galaxy potential, gravitational potentials, which is to say the shape of how their mass is distributed, is mostly dark matter, but then there's a significant amount of stellar mass and gas mass in a disk. And that shape is susceptible to particular resonances, particular ripples. Just the way, if you take a jar or a pot or a drum or something, or a bell, it's got a shape, it's got a size, it's got a material. You tap it, it has a particular tendency to ring. And we know that stars also ring, they also vibrate. And galaxies just have some resonant frequencies that make them susceptible to these spiral arms. And it's quite possible that the spiral arms can be affected by the gravitational influence of a nearby galaxy. But we also know that spirals exist in isolated disk galaxies. So it just looks easy to make, and you just have to sort of start them ringing, and they keep ringing.
Thank you so much. There's another question here about when you were relaying your radio astronomy observations. Do you encounter radio interference during these observations?
Absolutely, yes.
And how do you deal with them?
Yes, it depends on the kind of observation. For example, the LMT, the Large Millimeter Telescope, is it's taking measurements as a time series. It's not like an optical CCD where you might expose for 5 minutes or 10 minutes or even an hour, and you can't separate that into separate smaller pieces. You get what you get in an hour, and you can't tell when a flash of light that may have happened during that hour, when it happened. It happened sometime during the hour. It's in your picture. Instead, the radio observations that we make are actually taking data on a millisecond time scale. Very, very quick. It's like a movie. And so the interference tends to be time varying, and that makes it much easier to filter out. So we take our time series of the sky, and we have algorithms that look for a sudden spike in the time series, and we filter that out because most of those are from artificial interference. For example, a satellite passing overhead. With that said, it's getting worse and worse. The satellite problem is growing rapidly, harder to filter out, and the future is going to be significantly more complicated.
Are the what they call this the Starlink system, which is also affecting observations,
Yes.
radio astronomy observations?
Yes, Starlink has not been a major problem millimeter yet, but it is certainly a problem at longer wavelengths. They transmit at wavelengths of typically tens of centimeters. Ours is in the millimeter. But they have their transmission has lots of leakage into other wave bands that is getting closer and closer to the millimeter. And now there's new technology. There's constant international pressure from the commercial satellite sector to gobble up, to buy different parts of the spectrum. And radio astronomy has a few protected bands that are getting more and more squeezed and more affected by interference from the satellites. And the new technology is bigger and brighter and more interference than ever. So it's not an easy problem.
Thank you. Before I go to I think Mr. Dante Cruz De Jesus also has more questions, but before I go into that, there's a question here regarding the effect of the merging of what will be the effect of the merging of Andromeda and the Milky Way to our solar system? Yeah.
Yes, it might be nothing. It might be remembering that the space between the stars is so vast compared to the size of our solar system. So, for example, our solar system is a few light hours across, but the nearest star is 4 light years away. Stars very rarely hit each other. Only in the most dense environments do stars actually collide, like the center of the Milky Way Galaxy or the center of a globular cluster. But for the most part, when galaxies collide, the stars don't touch. They feel the gravity of the whole system. And it's that large scale gravity that will reshape, it'll take 2 disk galaxies and turn them into one elliptical galaxy. So the Andromeda galaxy and the Milky Way will no longer exist. They will become a new elliptical galaxy. And maybe in the process, there will be a starburst, and maybe there will be an active galactic nucleus with a supermassive black hole. That's a combination of the Milky Ways and Andromedas. But the stars themselves won't collide. And the planets going around those stars, many of them will just not even notice. It could happen that we will experience a collision with a star passing through our solar system, or maybe even hitting the sun. But the chances are pretty small.
And I guess we don't even know if humanity will still be here.
It's a long way away.
I'll just read the question because Mr. De Jesus had some 2 more questions here or comments. No? The first one is, sun's gravity exerts influence on solar filaments suspended in its magnetic field, which sometimes produce eruptions according to our previous guest, Dr. Pillay, in his webinar. Isn't this more like a demonstration of both magnetic acceleration and reconnection, respectively, in magnetic events happening with a star in the galaxy?
Well,
Yeah.
it is certainly true that the sun is a star in the galaxy and it is experiencing that magnetic acceleration and reconnection, no question. I'm not sure if that's what you mean, though. Are you asking about the larger context of galaxies and galaxies colliding?
Yeah.
What you say about the sun is absolutely true, but I am not sure I understand the context.
Okay, thank
Maybe
you.
it's in the third question. Can
Yeah.
magnetic
Can
positive
acceleration with the north-south poles orientation join gravity in accreting magnetized matter to the surface of a celestial body?
Let's see. It is certainly true that magnetic fields play an important role in compact objects, including young stars. And young stars have strong magnetic fields, and the magnetic fields certainly play a role in how the material is accreted onto them, including formation of jets that are observed to come out of young star formation regions, protostellar disks. For example, if you look in the Orion Nebula, which we all take pictures of and we all know very well, if you look in the Orion Nebula with Hubble or JWST, you will see lots of little tiny disks, some of them with jets coming out of them. Those jets are powered largely by magnetic fields in ways that are not fully understood, but it certainly has to do with accelerating the accretion process.
Thank you. In relation to that, may I know a layman's question? What is the role of black holes in galaxies and galaxy formation?
That is such a big open question. I wish I had the answer to it. It's a major question that motivates many people's work right now. One thing that we've learned in the last 20 years that's very important is that not only do most galaxies, major galaxies like the Milky Way or Andromeda, have a supermassive black hole in the middle. The Milky Way's is about 4 million times the mass of the sun. But the bigger the galaxy, the bigger the black hole. And that tells us that that cannot be by chance. There must be a physical reason for that. So somehow the black hole knows about the galaxy around it, or the galaxy knows about the black hole inside of it. Somehow either one of them affects the other one, or there's a third thing that affects them both that we haven't discovered yet. But there is clearly some physical connection between the size of the black hole and the mass of the galaxy around it. And that is something that my theoretician colleagues are working hard on, trying to figure out what's the key to unlock that mystery, but we don't know the answer yet.
Thank you, James. Well, here's a bigger question. How do you think the universe would end? Will it continue to expand forever?
All the evidence so far is yes, it will continue to expand forever and faster and faster. And that was the big surprise 20 years ago from mapping carefully the distance to supernovae, that supernova type 1A, which are good distance indicators, that let us measure the distances to galaxies, which let us measure the Hubble expansion rate over time. So we think we know pretty well how fast the universe is expanding now. If we look back in time, we expected that we thought it would be expanding faster earlier and slower now. It turns out it's the opposite. It was expanding slower before, and it's expanding faster now. And that means the universe is accelerating. That was the discovery of dark energy, which Einstein had predicted, but then was discounted for almost a century. But now it's come back, and we now believe that dark energy, whatever that is causing the universe to accelerate. And the fate looks as if not only will the universe not come back together to form a big crunch, but it will not even slow down. It's accelerating. And while the Milky Way Galaxy will not expand. The Andromeda Galaxy will collide with the Milky Way. That will stay as one big bound galaxy. The distant galaxies from us will all be further and further away.
Thank you. Before we proceed, I think there's one question, but I could not read it. But can I ask now the panelists if you have questions for James?
James, I don't know how to ask this question, but so receding galaxies, as we see it, are older galaxies, right? So, but if you have a massive galaxy, say for example, you have two galaxies that are receding, and then you have a galaxy here that's massive, and the galaxy that's receding close to it is being affected or pulled by gravity. So is it right to say that not all old galaxies are out there, but there are some that are closer?
I think what you're getting at, Imelda, is the struggle between the expansion of the universe and gravity working against that. Yes, it's a question of scale. On scales of roughly Milky Way Andromeda, that's the scale of about a galaxy cluster. Then gravity dominates. So that's why the Andromeda Galaxy is not flying away from us. It's close enough to us that gravity wins, even though we're both embedded in an expanding universe. But the Virgo cluster of galaxies, that's so the cluster itself is held together by gravity, but our distance from it, well, we're slowly falling in towards the Virgo cluster. But anything further than that, gravity is too weak to stop the expansion. So expansion always wins at scales bigger than roughly a supercluster of galaxies. So does that begin to address your question?
Yeah.
Okay.
James, I have more or less along the same line as Imelda's question. So if you're observing a distant galaxy and there happens to be a massive galaxy along your line of sight, so like a gravitational lensing galaxy, how does the intervening galaxy affect the redshift of the background galaxy?
It does not affect the redshift at all, fortunately. In fact, we're able, it affects the appearance very much. I showed you these images that are rings or strings or funny shapes that very distorted, right? So that the optical, let's see, the morphology, as we call it, the shape is very affected. The apparent morphology. The spectrum is not affected at all, fortunately. So if you point your telescope at one of those long strings or arcs, you get a spectrum that is just the same as if it weren't gravitationally lensed at all.
Got it.
Fortunately.
James, by the way, before I forget, I just wanted to thank you. Edwin and I were talking as you were giving your presentation of how you gave this presentation where any layman would understand what you're doing.
Yeah, your lecture was very clear and very accessible to everyone. And thank you for that. And it's no wonder that your astronomy course is probably one of the most popular on campus.
You are very kind. Thank you both.
And we would want to extend an invitation again to you, maybe for the coming year, to talk more about light pollution and astrophotography.
I would love to talk with you more about that and to hear about your experiences, including in the Philippines and also in the Boston area, and to put our heads together to talk about how to help turn back the tide.
Protect the night sky. And before we forget, thank you so much for showing those beautiful movies of the Milky Way. You took them yourself, right?
I did. I hope they came across okay. I know some of
Yes.
them.
Yeah,
They're
beautiful. Yeah.
beautiful.
Yeah.
And
Yeah.
also the circumpolar star trails. Those are wonderful.
It's so much fun, and we're so lucky to be
It's
able
like
to.
you were going warp speed. Thank you, James.
My pleasure. Thank you. Thank you all so much for coming. It's been a pleasure meeting with you all.
Are there any other questions from the panelists? I don't
Yeah,
think they are.
I
Yeah.
have one.
Yeah. Okay. Okay, Peter.
Yeah, just a follow-up question. After the merging of our galaxy and the Andromeda Galaxy, does this mean that we may see much more stars and eventually could change the current constellations that we currently see in the night sky?
Yes to both. Yes. The constellations will be long gone by then. The constellations that we know are, of course, the same ones that the ancient people across Asia and Africa saw thousands of years ago. But they are slowly changing, as we know. Not in a human, not perceptibly in a human timescale, not even in the course of civilization, but in a million years, yes. And a million years is nothing compared to how long it will take for the collisions to happen. So first, the constellations will be gone, just because the stars are all moving around the Milky Way. For scale, it takes the sun about 250 million years to do a full orbit around the Milky Way galaxy. So in that time, all the constellations will be mixed up because not all the stars are moving in a fixed system. You know, they're all moving at slightly different speeds. And so in a few million years, the constellations will be all mixed up. But the collision doesn't happen until something like 4 billion or 5 billion years later. When the collision happens, yes, imagine Andromeda getting bigger and bigger and closer and brighter in the sky, and then the stars getting mixed up. And yes, so the addition of the new stars will make the night sky brighter, and the formation of new stars from a starburst. It could be pretty spectacular. It's too bad we won't be here to see it.
Oh, thank you very much, James. We love your lecture.
Any
You're
other
welcome.
questions? Yeah.
Thank you.
Any other questions before we proceed? Well, if none, let me take this opportunity to thank you, James, again, all for your patience in answering all the questions from our viewers. And kindly allow me to present our ALP Certificate of Appreciation. It reads, this certificate is presented to James D. Lowenthal for the webinar entitled Bright Galaxies, Dark Skies, held as part of the ALP Astronomy Expert Speaker Series of 2024, given this 24th day of November. Signed by Mr. James Keventhi, President, and yours truly, Dr. Jose Aguilar, Vice President. So thank you so much again. And usually we take a group picture before we let you go. Can somebody please take a group picture?
All right. Okay. Whenever you're ready, guys. All right. So
Good.
here it goes.
Look at the camera.
Look at the camera.
Ay, wait. Wala yata yung ano. Nawala ba yung background ko?
No. All good.
Yeah.
All
Still
good.
there?
We can see your background. Okay.
Wait. Okay. Wait.
Andrew, how
Okay.
about you? Andrew, can you turn on your there you go. All right. Okay. 3, 2, 1. Hold on.
One more.
One more.
Good.
One more.
Yes, one more. And 3, 2, 1.
Thank you.
Okay, thanks very much. Guys.
James, thank you
James,
so
thank
much.
you so very
We
much.
can't thank you enough
Yes.
for taking the time from your busy schedule
You're welcome, and
So
share
thanks.
your-
much, James.
Thanks
your
to
Thank
you,
you,
and
James, for
thank you to you for your
joining
patience.
our
And,
webinar.
Thank you so
It's
much.
an honor.
goodbye, everybody.
Good night.
Goodbye.
Goodbye, James.
Bye-bye.
Have a
Right.
nice
Good night,
evening.
James.
Bye bye.
Bye.
Thank you.
Bye-bye.
Bye. Thank you so much.
So before we conclude today's webinar, I would like to thank all our attendees for joining us. We'll be sending your certificate of attendance by email for those who were able to join us today. By the way, this is the 26th webinar in our ALP Astronomy Expert Speaker Series since we started 2 years ago. Our first speaker was the late Dr. J. Pasakov on April 23, 2022. Our other esteemed speakers were Mr. Zolt Livey, Mr. Joe Rayo, Mr. Fred Espenac, Mr. Robert Reeves, Mr. Ken Crawford, Mr. Dave Eicher, Professor Matthew Barlow, Mr. Scott Roberts, Father Christopher Corbally, Mr. David Levy, Mr. J. Kelly Beatty, Imelda Johnson and Edwin Aguirre, Dr. Daniel Green, Dr. Heidi Hamel, Dr. Deborah Emil Green, Brother Robert McKay, Brother Guy Consolmano, Hilary Andales, Dr. Valentin Pillay, Mr. Wally Pacholka, Dr. Robert Nemiroff, Dr. Michael E. Brown, Dr. Jonathan McDowell, Dr. Brad Schaefer, Dr. Peter Jenniskens, and for today, of course, none other than Dr. James Lowenthal. We are so grateful to all our webinar speakers who very generously gave their precious time to share their knowledge and expertise to the world astronomical community. We can never thank you enough. And for those who missed all our previous ALP Astronomy Expert Speaker Series talks, you can view the video recordings of our past webinars at your convenience at our official ALP YouTube channel shown here. And also very exciting, our next speakers for our ALP Astronomy Expert Speaker Series. So on December 14, we will have a topic on the importance of preserving astronomical history. A very, very interesting topic by no other than Mr. John Briggs, astronomy historian and past president of the Antique Telescope Society. And next year, on January 18, 2025, we will have a talk by the editor-in-chief of space.com, Tariq Malik, Big Rockets, Artemis, and Starship. And another upcoming speaker has actually joined our webinar today, Alan Hale, the co-discoverer of Comet Hale-Bopp, the Great Comet of 1997. So very exciting. Please look at our social media page of ALP and the astroleaguefields.org for final announcements regarding these upcoming talks. But our next talk will be on December 14 on the importance of preserving astronomical history. Please join us. So thank you everyone for your kind attention. Stay safe and clear skies always. Bye-bye.
Bye, everyone.
Thank you.
Thank you.
Bye,
Send
everyone.
the
Bye-bye.
link.
Bye. Thank
Bye.
you.
Bye.
Okay.